Today we're going to learn about limits that come from the left. Before we do that, we're going to look at a visual example. Let's say that you are standing on one side of a basketball court, and let's say your friend says, let's play a game. So they say, okay, what I want you to do is I want you to walk halfway from where you are to the end of the court. You say, okay. So you go ahead and you start walking halfway. So there's your progress at the bottom of the screen. You've gone 30, 40, 50%, right? You're halfway to the court. Your friend says, okay, that's great, but we're going to continue the game. Now you're going to walk halfway from where you're currently standing, where your feet are, to the end of the court. So it's a new halfway. You say, okay. So you start walking halfway to the end of the court again, starting at the halfway court now, not at the beginning. So now you've gone 75% of the way. Your friend says, okay, I want you to do it again. Start from where you're at now, which is about the top of the three-point line, to the end of the court. You say, okay. You walk halfway from there to the end of the court. Now you've gone 87.5%. And your friend says, okay, walk halfway again. And now you're at the foul line. You walk halfway again. And you're getting closer to the end of the court. And so your friend says to you, okay, I want you to get to the end of the court. But in order to do so, you have to walk halfway each time. And you say, okay, well, all I got to do is keep walking halfway and eventually I'll get there, right? Well, no matter how many times you finitely, in other words, if you can count it, go halfway, if you physically were to keep trying to go halfway, you'd never end up at the end. You'd always be closer and closer, but never quite there. Here we're at 99% of the way. If you were to do it infinitely many times, then yes, you would actually reach halfway. We would each reach the end of the court going halfway. But what person do you know can infinitely go halfway? And eventually, you're actually going to die, right? So the concept we're talking about, though, is the limit. We keep walking to the end of the court, but we never actually get there. The limit is the value of the number that you're getting closer to. You may or may not reach that desired value. And in the case of the court, if you were to go infinitely many times halfway, you would get to the end. You'd reach 100%. But like we said before, that's impossible. No human can can walk infinitely many times. They're going to run out of time. And so you may or may not reach that end court line, but the limit in that particular case, let's go back to the visual, would be the end of the court. You'll never get there, but you're certainly always getting closer. That's the concept of the limit, getting closer to something. Sometimes you do get there, sometimes you don't. Another example would be if you're traveling and you're taking your family from New York to Los Angeles. You're driving towards Los Angeles, and eventually you will get there. Los Angeles would be your limit. It's the city you're getting closer and closer to as you drive further and further. Sometimes you get there, sometimes you don't. So again, the limit is the value that you're getting closer to. Let's take a look at some graphs. Today we're going to focus on graphs, and again, we're coming from the left for today. So here we have a graph. It's a piecewise function, two separate pieces. The first thing we're going to do in order to find the limit, of course we're not exactly there yet to define it, but what we're going to do for this activity is we're going to place a point on the graph and to the left of the vertical line x equals 2. Remember, vertical lines are x equals. So there's my point, somewhere to the left of x equals 2. Okay, now we're going to take that point and we're going to trace it closer and closer to the vertical line x equals 2. So here we can see that point getting closer and closer to x equals 2. Now, will it actually get there? No. Okay, we can keep recycling that over and over again and see that point getting closer and closer to 2. So the key is the point is on the graph, it's getting closer and closer to 2, and it's coming from the left. Now we want to figure out what y value or what f of x value the point is approaching or getting close to. Well, if we take a look at the values of the point, we see that x value in red is getting closer to 2. What's the y value, which is blue, getting closer and closer to 2? Even though there's a hole there, we can see that the blue value is getting closer and closer to a certain number, but never actually getting there. 2.9, 2.99, so on and so forth, as the red value x gets closer and closer to 2. If you said 3, you are correct. As the x value in red gets closer and closer to 2, the y value gets closer and closer to 3, even though it never actually equals 3 because we have a hole there. The y value that the point was or is approaching is called the limit. So in this case, the limit would be 3. The y value that it was getting close to was 3. Limit is the f of x value that a function approaches as x approaches a certain value. So when you talk about a limit, you're talking about a y value, but it's in terms of what x is getting close to. You can't have a limit without an x value getting closer to something. So they go hand in hand, although your answer will be in terms of y. When we say we place a point to the left of the line x equals 2, and we trace it towards the line x equals 2, there's a way of writing it, and that is x with the arrow pointing towards 2, and then we put a negative sign up and to the right of 2, and I'll notate that for you here. Okay, so now that I've got my pen and everything, I can notate this for you guys. So when we say, when it's coming from the left, the first thing you should notice, I'm going to underline that, is you're putting a negative, okay, up and to the right of the number. If we're coming from the right, we'll put a positive, and we'll talk about that later. The x value that it's approaching, okay, goes just down to the left of that. So you put the x value that it's approaching, and then you put the negative sign up and to the right to indicate you're coming from the left. If we put a positive sign there, which I'll erase this, but if we were to put something like this, that means we're coming from the right. And since x is approaching it, we write x and then an arrow. So what this means is x is approaching 2 from the left. This is another way of writing exactly what we mean in mathematical notation. And recall that function is just f of x. All right, that's a pretty quick, easy reminder, right? And so limit, we're just going to write as LIM. We're not going to write the whole word limit. And we're going to put all this together into one single mathematical expression that will make sense to you. So when we put it all together, we have the limit as x approaches 2. Remember, x arrow 2 means x is approaching 2. The minus up and to the right of the 2 means it's coming from the left, of f of x. So once you put the f of x after that, we're basically saying of the function f of x is equal to 3. Okay, and all this down here are the words we're talking about. Limit as x approaches 2 from the left of the function equals 3. It's a formal way of writing the limit, which is the y value that the graph is approaching as x approaches a certain value. Let's take a look at another example. Here we have another piecewise function, and we're going to start from the left. We're going to place a point on the graph to the left of the vertical line, x equals -3. So we have that green point down there, which is to the left of x equals -3. By the way, just so we know, the vertical line x equals -3 is right here. And as you notice, we're putting our point somewhere to the left of that. That's what we mean when we say put a point to the left of x equals -3. Now we're going to trace the point on the graph towards the vertical line x equals -3. Excuse me. So that green point is getting closer and closer to that line. Again, we talked about x equals -3. It's never going to get there. Why? Because there's a hole right there, and point to the hole right here. So that green point can never touch that hole. If it's a point on the line, which it is, it can never reach that hole. That's exactly what a hole is. There's no point there, so it has to stop right there. But again, when we're talking about the limit, we're asking what is the y value that it's approaching. And that's our third step. If we hone in on those values, we can see that the red line is approaching x equals -3. What is the blue line approaching? You can look at those values there on the screen and see that it's getting closer and closer to -4. Okay, and in fact, if you were to pause it right there, you would be able to see that that y value, of course I can kind of trace right here, is indeed -4, but it'll never get there because there's a hole there. Nevertheless, the limit is just what it's approaching. And so the point on the function is approaching -4, and therefore the limit is equal to -4. And again, we can write this analytically. In other words, we can write an equation for it. X is approaching -3, as we said before, from the left. And if we put that all together and read it together, the limit as x approaches -3 from the left of the function f of x is equal to -4, which is the y value that it's approaching. Let's look at a third example. We're going to get faster and faster as we go through these. Now we're actually going to read the question formally. So read this together. The limit, remember LIM, as x approaches 1 from the left of f of x. And evaluate means to figure out. So just like evaluate 2 plus 2 equals 4, we want to figure out, that would be 4, we want to figure out this limit. What is the y value that the function is approaching as x approaches 1 from the left? We're going to place a point on the graph to the left of the x value. So remember, the point has to be on the graph. Okay, and this time we're going to move that point together, and you can move it on your own. I'm going to give you the link below the video so you can click on it and follow along and do your own thing. We're going to trace the point on the graph towards the x value. Actually, this one is also automatic, but the point's getting closer and closer to that x value. And again, I'm going to kind of draw it on here. X equals 1. Now, again, notice that there's a hole at x equals 1, so that green point won't ever actually reach it because it's a hole. But the question is, what is the y value that it's approaching? This one might be a little bit trickier for some of you. But notice that it's always at 1.5, even when it gets to 1. It stays at 1.5. Well, this one's kind of trivial. That means it must be also approaching 1.5. And so it's not that difficult to see that it's still always going to be approaching that y value of 1.5 as x gets closer and closer to 1. So it's pretty obvious then that the limit must be 1.5. So sometimes it's right on the y value. It doesn't have to change from 1 to 1.5. It could remain at 1.5. It's just the y value that it's approaching. It's getting closer and closer to 1.5 as x gets closer to 1. As I said, we'll go quicker and quicker through these. Example 4, this says evaluate the limit as x approaches 3 from the left of f of x. Okay, again, we're going to place a point to the left of the graph, and this time we're going to actually do that ourselves. You can actually touch the point and you can move it yourself. I'm going to do that myself. I'm going to move from left to right and get closer and closer to that point. If you want to, you can select that button in the top right so you can see your particular x and y values. As x's get closer and closer to 3, what do you think the y value is getting closer and closer to from the left? If you said -2, you would be correct. So I'm kind of doing all the steps already. It's telling me to drag the point, which I'm certainly doing myself. The point of this particular one is you can kind of see that it actually gets to the y value. Okay, it actually ends up being -2 as x equals 3. So sometimes it ends up being the y value, and like we said before, that's completely fine. The y value can be equal to the limit. It doesn't have to be, but it can be. Let's go to example 5. Okay, what I want you to see right off the bat, this is kind of tough to see, but this is 0.6. It's hidden by the line. So the y value there is 0.6. Just so you know. This question is asking what the limit is as x approaches 0 from the left. So if we approach 0 from the left, we're going to put a point. This time I'm not going to use the crosshairs, but can you see what the y value is as x approaches 0 from the left? And again, just in case you forgot, x equals 0 is down here. So we're seeing what the y value is as it approaches 0 from the left. And that's why I gave you that hint before, because as you can see, it's approaching 0.6. It's staying on 0.6, but that's okay. It's still getting closer and closer to 0.6 as x comes from the left and moves to the right, it's still getting, it's approaching that value, it's staying at that value, however you want to say it. And so therefore the answer is, let's get rid of that. The answer is 0.6. Okay, again, we can go back and see that y is getting closer and closer to 0.6 as x gets closer to 0. It's not actually getting closer to 0.6, is it? Because it's always 0.6. It's 0.6 out here, it's 0.6 here, but it's approaching that, or it's staying at that value. It's not getting close to any other value for sure, so the limit would be 0.6. Let's look at example 6. Okay, so let's see the limit as x approaches 1.5 from the left. We're going to do this real quick. As x gets closer and closer to 1.5, we'll use the cross hairs this time. From the left, what do you think the y value is getting close to? Well, it's obviously 1, right? Because the point's actually equal to 1 there, and that's what it's getting close to. Like I said before, the y value doesn't always equal the limit. Sometimes they're two different things, but in this case they are. So the answer is 1. Example 7. Let's see what the limit is as x approaches 0 from the left. Well, here's the problem, folks. I can't come from the left, okay? If there is no graph on the left-hand side of 0, we're trying to find the limit as x approaches 0 from the left, but there's no graph there. So when there's no graph there, there's no possible way I can approach from the left. If we can't approach from the left, then there is no limit, you see? So sometimes that happens, okay? And when that happens, when there is no place to come in from the left or from the right or whatever, we say the limit is undefined. Now, certainly from the right, we can see that it's approaching 3, right? But there's no way to come in from the left. This is called a one-sided limit. It only exists from the right, it doesn't exist from the left, and so again, we say it's undefined. The graph has no x values on the left, therefore it's undefined. So there is our reasoning. Let's go to number 8. This one is an oscillating graph. We're going to again figure out the limit as x approaches 0 from the left. So I'm going to take this point, and coming from the left, it does oscillate, but notice the oscillation gets smaller and smaller, and if we are able to zoom in with the software, by the way, this is GeoGebra, I failed to mention that. It's an excellent program. I would highly recommend it. If anybody has any questions about GeoGebra and how to use it, let me know. I'd be happy to help you out. But anyway, as it approaches 0 from the left, it's getting the y value is getting smaller and smaller and smaller and smaller, and oscillates. And in fact, we can see that it does approach 0. Even though it oscillates, the oscillations get smaller and smaller. This is a tricky conceptual one, but indeed, the y value will get closer and closer to 0. Again, I would encourage you to do this yourself, and you can zoom in as much as you'd like and see, no matter how far you zoom in. And in fact, the more you zoom in, the more you see that the y value will approach 0. So for the limit is 0. And the same is going to be true from the right. Example 9. This one's a little tricky because we're still going to 0 from the left for the limit, but when we try to drag this point, we notice that the y value will always bounce back and forth between, looks like, negative 0.3 and 0.3. It will never actually converge like the one before. It will always bounce back and forth, and so no matter how much we zoom in, because those oscillations have a definitive height, in other words, they're 0.3 at the top and negative 0.3 at the bottom, as we go to 0, it will never actually approach 0. It will always oscillate. We can look at that equation for that function and be able to tell that later on in this class, but for now, you can see by the graph it will never actually approach a particular value because it'll always bounce back and forth. This one is crazy, is what we have there, but ultimately it's undefined. We're going to be using this graph for the remaining examples, and we're going to do the limit as x approaches negative 2, again from the left, that's the negative sign, approaching negative 2 from the left. Okay, so we're just going to drag our point, and we can see as it approaches negative 2 from the left, it's equal to 1, right? The y value is approaching 1. Again, we're going to go through these real quick. If you have any questions, let me know, but I want to get this finished for the sake of time. Now let's do the limit as x approaches 0 from the left. So as we approach 0 from the left, be careful. Okay, again, we're looking at what the y value is approaching as x approaches 0 from the left, and it looks like negative 0.5, right? Not 0, but negative 0.5. Again, it's this value down here that it's approaching. So negative 0.5 is going to be the definitive answer. That's all you need to know for that one. Example 12, same graph. We're going to do the limit as x approaches 1 from the left. Now, here's the thing. If we're approaching 1 from the left, we're putting a point on the graph. We're tracing it from left to right as it approaches 1. It's approaching 1.5, right? The y value is approaching 1.5. We're not concerned about the actual function value. We know that f of 1 equals 0. We're focused on what is the y value it's approaching as x approaches 1 from the left. The answer is going to be 1.5. So just be careful to distinguish the function value from the limit value. Let's approach 2 from the left. As we approach 2 from the left, again, notice, okay, so yes, there is a point right here at 1. I don't know if I can get, well, I have to refresh that. I don't know if I can land the point right on it and keep it there. There we go. But if we're trying to get to 2 from the left, notice that just to the left of the graph, there is no graph. Okay, there's nowhere to put that point. We talked about that before. Since there's nowhere to put the point just to the left of x equals 2, and there's no limit value. So we say the limit doesn't exist or it's undefined from the left. Now we're going to use letters or variables, which is completely fine. In this case, we're going to find the limit as x approaches a from the left. Okay, so as we approach a from the left, what is the y value it's approaching? Well, we don't have any numbers, but we can see as we go to a from the left, the y value is approaching j. Sometimes a limit is a variable. That's completely fine. It's just consistent, again, with the definition of a limit, which is the y value that it's approaching. Okay, then we're going to do another example with the same graph, limit as x approaches c from the left. So as we approach c from the left, we see the y value approaches L, okay? Again, it's not this point in the middle, it's what it's approaching, not the actual function value, and it's indeed approaching L. And then one last example, let's do the limit as x approaches D from the left. As it approaches D from the left, sometimes my students say, well, where's the point? You don't have a point right there at D. Well, there's still a point there in the graph, it's just not emphasized. Everywhere on a graph has points, okay? Some points are emphasized and some aren't, but it's still a point. That's how a graph is made. It's just a bunch of points. So anyway, as x approaches D from the left, like this, we can see that the y value approaches k. And that's it. You can take a quiz later if you want yourself. That's it for now. Next, we'll be studying limits from the right. If you have any questions, let me know.